Hey everybody, this is the notes for lesson 3 from unit 2 where we're going to deal with symmetry and end behavior. So make sure that you're all set to take some notes. Pause if you need to, rewatch, and let's get rolling here. First to begin with is the difference between even functions versus odd functions. Even functions, well, they're going to be something that's called reflection symmetric. You're going to be able to kind of fold this graph in half over your y-axis. So for example, you've got this folding line right here, which is the y-axis. You can kind of fold back and forth. It kind of looks like so. So parabolas are good examples of even functions like that. Odd functions, on the other hand, are rotation symmetric, and the way that that kind of described is I like to think about is you put like a big spoke right through the middle of the origin. You can turn this into a pinwheel. It will spin around 180 degrees, so on and so on, and reproduce itself just like so. So that's the difference between odd function versus even function in terms of their picture. All right. If you wanted to do a test to see, oh, do I have an even function? Do I have an odd function? The even function test looks like so. F of opposite of x. So you put a negative x in, or the opposite of x in, you get out the original function. So let's take a look here. F of x is equal to 3x squared minus 5. If I'm going to try to figure out, well, what is f of the opposite of x? Throw in a negative x for x. So I reproduce 3 just like so. X squared is going to be a negative x, and I'm going to copy through that squared, and then minus a 5 is a minus a 5. All right, well, let's clean it up ever so slightly here. Let's see here, 3 times a negative x squared. A negative x squared, anything squared, anything times itself is going to become positive. So we're thinking through and we say, oh, okay, well, this part right here, a negative x squared, isn't that the same thing as just regular old x squared, since they're both going to become positive? Sure, absolutely. So this means I have a 3 times x squared and then minus a 5. And you're like, I can't do anything else with that, and that's because take a look at what we have. 3x squared minus 5, 3x squared minus 5, that is the same thing as f of x. So if I recopy this down here, f of negative x is equal to f of x, that tells me I have an even function. So I do that test right there. If I substitute a negative x in, I get out the original problem. Over here, the test is for odd. If I'm trying to figure out if the function is odd or not. Well, it says if I put in a negative x, I should get out opposite of the function. All the signs should kind of flip-flop. So let's give it a try. F of the opposite of x, f of negative x, is equal to a negative x, oops, didn't do that right there, sorry guys. It's equal to negative x on the inside of the parentheses cubed minus 2 times negative x. All right, well, again, let's kind of think through this. If I have a negative x raised to the power of 3, that's the same thing as saying negative x times negative x times negative x. A negative times a negative times a negative is still a negative. All right, so this is going to be the same thing as a negative and then x cubed. All right, look over here. A negative 2 times a negative x, negative times negative is positive. That's positive 2x. All right, well, I look what I started with. I started with an x cubed, and now I have the opposite of x cubed. I started with a minus 2x, and now I have a positive 2x. All those signs flip-flopped. If all the signs flip-flopped, what I could do is I could factor out a negative sign. If I factor out my negative 1, I have a regular old x cubed, and then I have a minus of 2x, and that is the original function. So therefore, I can conclude that f of negative x is equal to the opposite, a negative, of f of x. So I was able to flip my sign around on every single term. So therefore, I have an odd function. So mathematically, that's how I can prove that's going on. With a visual, with a graph, I can take a look at those guys. All right, just a little recap as to what we just did. Some nice little notes, some quick tips for you guys right there. What we need to do is replace every single x with the opposite of x every single time. If everything stays the same, everything's normal after you go through all of your mathematical abilities, then you have an even function. If all of your expression turns into the opposite signs, everything's going to be flip-flopped, then it's an odd function. And if you have some kind of combination, if nothing is, one of those two things isn't happening, then it's a neither. You don't have an even, you don't have an odd, and that happens also. All right, last little thing that we have on this particular lesson is what's called end behavior. And end behavior just means you're going to look to the far left, far F-A-R left, and look to the far right. All the way to the left and all the way to the right to try to figure out what's going on with this graph. So if I look at this guy right here, if I look to the far, far left, that's this side right here, the arrow's pointed up. And then if I look to the far, far right, this arrow's also pointed up. Therefore, I would say in that particular graph that my end behavior would be up, up, just like that. Left side goes up, right side goes up. All right, let's look at another one over here. This guy right here, if I look to the far left, this arrow points up. Look to the far right, this arrow points down. So the left side's up, right side's, that's not up, that's down. So then this end behavior over here would model the direction of up, down. Now that's pretty easy, that's pretty straightforward. Just look and decide what direction are those arrows pointed. We can do better than that. We can do better than that. And that's what's called limit notation. Yes, limit notation. So limit notation is when you actually decide and map out how this graph is looking. So if I look at the very first one right here, very first graph that I had right there, I know that as I looked to the left, I also looked to the up. So I need to kind of map that out mathematically a little bit. And with limit notation, I'm going to spell this out. This says the limits, L-I-M, I abbreviate that, as x goes to the left. As x approaches, well, what number is to the left? The number to the left is negative infinity. So as x approaches, that's what that arrow stands for. As x approaches negative infinity, the entire function, whatever that name is, we'll just call it f of x for now, is going to go up. Well, up is what direction? Up is positive infinity. So as x approaches negative infinity, the function goes to positive infinity. Okay, that right there is going to correspond to that blue arrow. All right, well, let's try another one. How about the limits as x approaches positive infinity? The limit as x goes to the right side. Well, the function then is going to go up, 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 up. So it's also going to go to positive infinity. That corresponds to the right side of the graph. So this right here in green matches up with this guy right there. Because as x gets bigger, bigger, bigger up to positive infinity, the whole function gets bigger, bigger, bigger up to positive infinity. Nice. Okay, let's try another one here. This graph right here, I'm going to say the limits as x approaches negative infinity of whatever the function is, f of x, is going to go up. So it's going to equal positive infinity. And then the other side of this, the limits as x approaches positive infinity of the function f of x, well, this time it's going to go down, because if I go up to positive infinity for x, if I go to the right side of the graph, it's going to go down to negative infinity. And just to kind of map out what I mean by this part right here in yellow is the left side of the graph. That's this part right here. And then this side over here in orange, that represents this part of the graph, the right side of the graph. Okay, well, let's try them just a little bit more challenging here. How about these two graphs? All right, the first one, if I kind of look at this side of the graph, all right, in yellow right there, I could say the limits as x approaches negative infinity of the function. Well, it's not going up and it's not going down. It kind of flattens out to a horizontal asymptote, so it flattens out to negative 2. So sometimes it's not positive infinity, sometimes it's not negative infinity, sometimes it's actually some value if it flattens out to some type of asymptote. On the other side, I could say that the limits as x approaches positive infinity, as we go to the right side, the function itself is going to go, it goes up, 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 up. So that's positive infinity right there. So that's this part of the graph is going to match with this guy right here. Awesome. Okay, one more for you. How about these guys right here? If I said this side of the graph, I could say the limits as x approaches negative infinity, because I'm going to the left side of the graph, of the function is going to equal, well, it looks like it flattens out to that horizontal asymptote at negative 3. So that's what that left side goes to. All right, last one. How about the limits as x approaches positive infinity? We're going to be looking over here at this part of the graph in blue. Okay, so as we get bigger on the right side, the function itself, it's not going up to infinity, it's not going down to negative infinity. It looks like it flattens out to that horizontal asymptote of 4. All right, so that's what that part is, that blue part right there. Feel free to pause, feel free to take extra notes, and we'll see you next time. Bye.